Hello, welcome to the fourth day of online course on astronomy. Today we'll be speaking about galaxies and the structure. Here is a picture of the night sky, and you will see that somewhere here there's a fuzzy nebulous object. To give you a perspective of where we are, this is the Cassiopeia, and somewhere here this is the Andromeda constellation, and here we have this is the patch of the sky we are looking at. And if I blow into it, I see that nebulous object becomes even more clear, right? So what are nebula? Nebula is from the Latin word cloud. In the past, the word nebula was used for extended fuzzy astronomical objects. They could be star-forming regions, supernova remnants, planetary nebula, globular clusters, galactic clusters, or galaxies, right? Here are some images of nebulae. And today we realize that a nebula is an interstellar cloud of dust, hydrogen, helium, and other ionized gases. Nebulae are often star-forming regions, such as the Eagle Nebula, or stellar remnants, such as the Crab Nebula. Right? This is the Crab Nebula, stellar remnant, and these are star-forming regions which are nebulae. So in earlier times when they saw these fuzzy objects, they did not know what they were. And today we realize that when we zoom into it with better telescopes, we see that some of these nebulae are actually galaxies. Like this, the nebulous object which we're looking at was this Andromeda galaxy. So what are galaxies? Galaxies are large collections of star dust and gas. And by large, I mean there should be billions of stars in it. A collection of stars, a cluster of stars with million stars will not be considered as a galaxy. It has to have billion, 10 to the power of 9 stars or 100 billion stars. Typical masses of galaxies are of the order of 10 to the power of 9 to 10 to the power of 12 solar masses. And let me remind you, the mass of Sun is 10 to the power of 30 kg, 2 into 10 to the power of 30 kg. Typical sizes of these galaxies are about 30 kiloparsecs, where kiloparsec means 1000 parsecs, and 1 parsec is 3.26 light years. And 1 light year is the distance traveled by light in 1 year. So the extent is typically approximately 30 kpc, or in terms of light years, it is 100,000 light years. Let's take into the historical advances which led us to understand what galaxies are. Here is a short historical perspective. Initially, humans thought that Earth was the center of the universe. We had these geocentric theories, which was supported by the mathematics of Aristotle, Ptolemy, and physics of Aristotle. Then comes Copernicus in 1543. He gives us the heliocentric theory, where he placed the sun at the center, not the Earth of our solar system. And it took more time for people to accept this theory. Copernicus gave out his theory, released his book only on his deathbed. He was afraid that people would ridicule him, so only when he was dying, he gave out his heliocentric theory. And it was accepted only in the mid-17th century. 1610, Galileo turned his telescopes to the Milky Way. Here is the picture of a Milky Way, a band of sky where you have innumerable stars. In India, it's called Akash Ganga. There were a lot of myths that this was the river of milk. That's why the name Milky Way or Akash Ganga. the Ganges of the skies. But when Galileo turned his telescope to this Milky Way, he saw that there was no fluid there, but there were innumerable stars, lot of stars, and the fuzziness came from the having so many stars in the same place. William Herschel in the 18th century gave his first map of our Milky Way, which is given here, and he realized that the sun, it was a disc-like structure, but he thought that the sun was at the center of the galaxy. So then it was believed by late 18th century that Milky Way was a galaxy, and there was a debate then um, whether this was the only galaxy or there were many galaxies. Shapley in 1918, he looked at the distribution of globular clusters and showed that they have a spherical distribution, and the center of this distribution of globulars is not where the sun is, but somewhere else. And he concluded that sun is not at the center of our Milky Way galaxy. So it was from late 18th century, early 19th century, people believed that Milky Way was the only galaxy, and there was a raging debate between astronomers, and the famous one is the one between Shapley and Curtis, where Shapley thought that Milky Way was the only galaxy, while Curtis believed that there were more galaxies than our Milky Way. This debate was settled in 1920s by observations of Hubble and Emerson and Slipher, where they resolved stars of the Andromeda galaxy, and through spectroscopic measurements, they could measure the distance to this Andromeda nebula and realized that this was much, much further away than the extent of our Milky Way. So they realized that Andromeda galaxy was not a part of our Milky Way, but an external galaxy. They looked at some Cepheid variables there and could estimate the distances to Andromeda galaxy. So this settled the debate in favor of Curtis, and it was realized that Milky Way is not the only galaxy, but there are many, many galaxies. So here's the picture of a mosaic of galaxies. They come in different shapes, different colors, and different sizes. Let's have a closer look at them. Notice this galaxy. This is a spiral, beautiful spiral galaxy, and these are lovely spiral arms. Here's an elliptical galaxy, and here is a spiral galaxy with a bar feature in it. And then what we see here is an irregular galaxy, a galaxy which doesn't have any form at all. It looks a weird, freaky object. Here we are looking at the galaxy edge-on, and notice that there is a glow here coming from the bulge. It has a disk and it is a halo. So the question is, why do galaxies look different? Why do they have different morphologies? Why do they have different colors? And the answer to that is what we will see as we proceed. One simple answer could be, we could be seeing these galaxies at different angles. When we are looking at an elliptical galaxy face on, you would see it as an elliptical one, but when you are seeing it edge on, then you may see it as what you see on the right here. Similarly, spiral galaxy face on would show you the spiral features, but when you look at it edge on, it would look very different. So the angle from which we are looking at these objects could make it look like a circle or ellipsoid or elliptical and so on. So once it was realized that there were many galaxies other than our Milky Way, people started observing them, and Hubble gave a morphological scheme of these galaxies. This is called the Hubble's tuning fork diagram, given in 1936, where he distributed galaxies essentially into three bins: ellipticals, spirals, and lenticulars. Spirals, he broke them into two: normal spirals and barred spirals. So spirals which had a barred feature in it, and spirals which had no barred feature. So when ellipticals were from E0, E1, E2 to E7, E0 were the circular ones, and E1 was slightly elliptical, E2 more elliptical, and E7 was the most elliptical one. And lenticulars, SO galaxies, they have a bulge, they look like ellipticals, but they have a disk in it, but a featureless disk. So though this was just a morphological scheme, people started believing that this was the evolutionary scheme too. They thought that the galaxies are born spherical, and due to rotation they bulge at the equator and they become elliptical, and greater the spin velocity they would get more and more elliptical, and then a disk would appear, and for certain reasons, perturbations, the spiral arms would come out of it. So people thought that they were born as spherical E0 galaxies, which became E1, E7 due to different rotation speeds, and then they became the lenticulars and then the spirals. But this is not absolutely true. We would see that spirals can also merge to become ellipticals. So here's Hubble's galaxy classification scheme with actual pictures of galaxies. Here we have these beautiful images taken at present times with E0, which looks like a circular one, E3, which is elliptical, E6, which is even more elliptical. Then we have SO galaxies and SA, SB, SC, SBA, SBB, and SBC. And we have irregulars here. So notice how Hubble classified SA, SB, and SC. In SA, the nucleus, the central bulge is pretty dominant, and spiral arms are closely packed on it, they're closely wound. While SB, the central nucleus becomes smaller and the arms open up, and SC, the central nucleus becomes even smaller and the spiral arms open up even more. Similarly, you have S with capital B, A, S, B, B, and SBC, which give spiral with bars in it, where arms are closely bound, spiral bars with arms slightly open, and even more open. And this Hubble's classification has been improved upon by Divacular and so on. And Hubble believed that essentially we have ellipticals, lenticulars, and spirals. Spirals of two categories: barred spirals and normal spirals. And he observed that there were certain irregular galaxies, but he said that there were not many of these, and probably these were the ones where there was not sufficient mass, so they could not form a complete proper galaxy. And he avoided studying them mostly. But there were some people at the time, like Zwicky, who were more keen to study these irregular galaxies. They were wondering, why do these galaxies have peculiar, strange shapes? So why do galaxies have different morphologies? One of the arguments was what was given. And another one I'd said is, like I'd said, you are seeing from different angles, so you see different features, different forms. Like if you have an ellipsoidal one, seen from one side it could look circular, but seen from some other it could look elliptical. But there's more to that. What has been realized now is most galaxies have massive black holes at the center, and the bulge of the galaxy is directly proportional to the black hole mass. So here's a picture of as your central bulge increases, your black hole mass also increases. So the bigger the black hole at the center gives you a bigger bulge. And if the bulge is dominating over the disk, then you will see it as an elliptical. But if the bulge is small right at the center, you will see the spiral features more and you will see it as a spiral galaxy. Other than that, uh, galaxy interactions play a very important role, which we shall see as we proceed. Let's look at the background in early history. Earlier, once Shapley and Curtis's debate was settled by observations of Hubble and Emerson that there were more galaxies other than the Milky Way, people started believing that these galaxies are unevolving island universes. These galaxies do change their shape, but in our lifetimes, we don't see the changes. From day to day, or over years, or over 100 years, we would not see any change. The changes in galaxies would come over millions of years. So they were seen, and they were seen to be separated by very large distances. So the island universe theory came up, where they thought that galaxies were isolated, mostly unevolving island universes. And this was due to the lack of high quality imaging and spectroscopic data, which was not there. Today we have high quality imaging data and in different wave bands. And the detailed theories of stellar evolution, nucleosynthesis were not discovered yet. And one blind spot which people had was there was a sheer disbelief that gravity could produce such exotic structures such as tails and bridges. So people wondered how could such features in galaxy come, and they attributed to various things. They thought it could be magnetic fields in galaxies which could create it, or various other things. But it was essentially gravity which was acting at large distances, which was creating these exotic features in galaxies. So here's an image of the antenna. This is an image of a galaxy which is called NGC 4038 4039, also called the antennae, because they look like the antennae of a cockroach. You can see these two features here, and you can imagine a cockroach sitting here. And if we do a simulation here, you'll see how these things are formed. So what we are seeing here is two spiral galaxies coming and merging, and at one stage they are forming these antenna. So how are these n-body simulations done? These simulations are done by uh, solving. Yes, we have a set of n particles, mass particles, the stars, and we write the equations of motion, which is given by this Ri double dot, which is acceleration, is equals to summation of all the forces acting on the ith particle. And when your n is 2, we can get interaction between two masses, n equal to 3 masses, and n goes into millions, which is the million body problem. But the interesting thing is when n is up to 2, you can solve these equations. But when n is 3 or more than 3, we cannot find a complete closed form solution, though numerical solutions can be formed. And the problem becomes even more difficult as you go from n goes from 3 to 4, 5, and into millions and billions as you do for a galaxy. So we have to resort to solving these equations on a computer. We have got a lot of insight into uh, galaxy interactions by using simulations, and we see that in nature galaxies collide. And how do we define a galaxy collision? A galaxy collision is a close encounter that has a significant effect on the galaxies involved. So the interesting thing is, the in this field, a miss is as good as a direct hit in the field. By this I mean, when galaxies come close to each other, if they hit each other, but at very high velocities, they would not make any damage to each other. They would just comb through each other. But when they come close to each other, they may not go through each other even if they go past. But if the relative velocities are small, then they create havoc and they tear each other up, and there's a lot of exchange of matter from one to another, and it could also lead to merging of galaxies or disruption of galaxies and so on. So a near miss is as good as a hit in this field. It involves tremendous amounts of energy and results in important evolutionary effects. One, we should realize that it's not a high energy phenomena because the velocities are small, and these take over a long periods of time. They are extremely slow. So we can calculate the masses, two galaxies M1 and M2 of 10 to the power of 12 solar mass each, and which gives us 2 into 10 to the power of 42 kg. And if the relative velocities is about 300 kilometers per second, we can calculate and get energy released is about 10 to the power of 53 joules. These energies are comparable to the binding energies. So when galaxies come close to each other, and when there's so much of energy, 10 to the power of 53 is involved, this is equivalent to the binding energy. So this could lead to disruption of galaxies. But see, the 300 kilometers per second is 0.1 percent of speed of light. So the velocities are small, and it takes over 100 billion years, 300 billion years. So it's a extremely slow phenomenon. So when galaxies come close, tidal forces act at gigantic scales, resulting in formation of tails and bridges. Conditions for formations of tails and bridges are: the galaxies should approach each other in parabolic or highly eccentric orbits or prograde orbits. Galaxies should not penetrate much. So, uh, and for galaxy mergers, when the galaxies should approach each other with relatively small velocities, and yeah, so depending on the initial conditions, the stars gain or lose energy. Stars which gauge energy move outwards, while those which lose fall inwards, and in general, a star gains energy. The increase in overall energy loosens them and makes them disrupt. The increase of internal energy of the galaxies is at the expense of the orbital energy, which results in merging. So we have a simulation here of two spiral galaxies which merging to form these beautiful tails and bridges. So some interesting aspects of galaxy collisions: most of the matter involved doesn't collide with anything. There's a very small probability for a direct star-to-star collision, and the collision probability is about 10 to the power of minus 15. The gas components collide in rich galaxies. So these probabilities can be calculated. The cross-section of Sun is 10 to the power of 17 meters squared, and the surface density of stars near the Sun in our solar neighborhood is about 10 per light year square. That is 10 to the power of minus 32. And so 10 to the power of minus 30 divided by 10 to the power of 17 will give us this 10 to the power of 15, which is the probability of star to star colliding. And when the gas components collide, it changes the thermal state of the galaxy. Here's again a simulation of this is the NGC 4676, and this is also called the mice because it looks as though there are two mice which are sitting here. This is the tail of the mouse, and here is a simulation of the two, where you have seen two galaxies coming, spiral galaxies interacting and merging to form one huge elliptical galaxy. So what we see here are elliptical galaxy which is being formed by the merger of spiral galaxies. And this is the thing which we are seeing. This is the moment which we see right here, right? So the simulation so beautifully recreates the same picture which we get of these two. So this is showing the merger of spiral galaxies to form an elliptical galaxy. This is the moment of the interaction which we are seeing now, but as time progresses, these two objects are going to end up into one big elliptical galaxy. And what you notice here are stars being thrown out, right? Those which gain energy get thrown out, and some of them fall back, and there's a whole churning of the whole. So you have two spiral galaxies which come and they merge, they mix up each other, and they settle into a big elliptical galaxy. And if you notice clearly that there are shells sitting inside, and this can be seen by an image of an actual giant elliptical galaxy, and you can see similar shell-like features which you see here. And here is the same galaxy which I showed in the previous slide, where you see that at the center there are many nuclei sitting there. So this apparently is a merger remnant of many galaxies. It's just consumed, taken in many galaxies and settled up as a large elliptical galaxy. As of now, we realize that galaxies do merge, they interact at an individual level, two of them, and so on. But let us also see the effect of environment on the galaxy morphology and how does it play a role in evolution of galaxies. So our Milky Way galaxy belongs to a local group of galaxies. There are about 54 galaxies there. Milky Way and Andromeda are the two major galaxies here. Andromeda is twice larger than our Milky Way. And they are, as of now, the number is 54 galaxies. And this is called the local group. And local groups join together to form larger clusters. Ours belongs, here is the cluster of the Virgo cluster, and this is the Coma cluster. And you look at these images, these are clusters of galaxies where there are many, many galaxies. In the Virgo cluster, comprises of about 1,300 galaxies, which is a fairly heterogeneous mix of spirals and ellipticals. And Coma has over 1,000 identified galaxies, mostly ellipticals and lenticular galaxies, and a few spirals of younger ages, and many of them are probably near the outskirts of the cluster. So it is interesting to see whether at the center of the cluster do we see more of ellipticals or more of spirals or and so on. And this could give us a key into how the environment plays a role in the galaxy morphology and its evolution. Here are certain images of how, as a galaxy plunges into the cluster, the ram pressure stripping leads to outflows. This is a spiral galaxy ESO 137001 as it moves through the heart of the galaxy cluster Abell 3627. And you see these outflows, and similar outflows we can see in some more galaxies. These beautiful. And here's an animation which shows what is probably happening. So as this galaxy moves into this cluster medium, so the cold gas is driven out, and it leads to the stripping of cold gas from this. Okay, the animation, yeah. Stripping of the cold gas, and it could lead to quenching of star formation. So when galaxies interact, the so these are the environmental processes which could lead to deformation of galaxies, enhanced star formation, merging, and the terms these days used are dynamical harassment, starvation or strangulation, or cannibalism. Harassment is when two galaxies go past each other and one disturbs the other and totally deforms it. Starvation is, we've noticed, as there's an outflow of cold gas. Uh, the raw material for stars is reduced, right? So these are termed as starvation or strangulation, where you are stripping it out of gas. And cannibalism is when massive galaxies, they merge with smaller ones and take them within it. So with this, we'll come to the end of this lecture. I hope you've enjoyed it. Thank you.